Hey guys, we're going to do a review today over thermo. And with thermo, an important thing to note for this year's AP exam is that thermo falls into two different units in the AP curriculum, the way they write it. So we're really focusing on what we would call thermochemistry, but not the thermodynamics part. That means a lot with enthalpy, bond energy, breaking, making, which is a lot of what this stuff is here. But you're not going to see entropy, free energy. You're not going to be connecting that with kinetics. You're not going to be doing the calculations between delta G and K. So that's still on this document. So I'm going to kind of skip over it and ask you to do the same. I just really like the way this document looks, and there's really no reason to recreate it. Just do what we need to do. So with thermo, one of the important things that we said first, we said it last, we talked about it in class, we tried to show it with different magnets, was that it's all about the energy related to bonds. So when we break bonds, it requires energy because it's two things that are already stuck together. I'm forcing them apart. It requires energy to do that. So that is an endothermic process, or to get your reactants to separate. It's always the uphill part of our graph. And then after they have been broken, we are making some new energy as we form bonds. It's releasing it. We can also think of that as saying allowing things to come back together. So we've got our uphill and our downhill graphs on this. One piece with that is sometimes people jump to the wrong conclusions. They see a certain number of bonds on the left, a different number of bonds on the right, and kind of guess whether it's going to be endo or exothermic just based upon the number of bonds. Well, there is differences in bond strength. There's differences in bond type. There's lots of different factors that could mean, even if I'm only breaking a few bonds, but I'm making a lot, where one could be greater than the other, and we can't see that. So we really have to rely on data for this. We have to rely on graphs. If they're showing us graphs for this, we don't just count the number of bonds. And even sometimes with the synthesis or decomposition reactions, so two separate things become one, we think we're only forming bonds, therefore it has to be exothermic, or we think in a decomposition we're only breaking bonds. But in doing that, we are breaking bonds apart, but they might bond together in new ways. The atoms of, if oxygen is one of our products, for example, the two O's coming together is making a bond that's fairly strong. So there might be a lot of energy still released, even though we think about things we're just breaking apart or things just coming together. The other piece is that here I use the term bonds, and that's very important. This also connects with IMFs. So when things dissolve, we break the bonds holding our ionic compound together maybe, or we break the IMFs holding our covalent compound together. As they mix, we make new attractions between them. Those new attractions that are made, even though they're not chemical bonds, they do release energy. So that is an important piece here. It connects with maybe a little bit with kinetics, but definitely with bonding, definitely with IMFs. And since we're looking for fewer questions, we're probably going to see more connections between topics like that. So enthalpy, or the focus of thermochemistry, is about bond energy or the heat content. It's going to be getting hotter or colder because of this. So we can look at it. We've got it 5 different ways that we can see here on the screen. We could be told with a balanced equation that there's a certain delta H for the process. If we know the delta H for the process, I can relate kilojoules to moles, and I can still relate moles to grams, or moles to molarity, or moles to volume of the gas. So in a balanced chemical equation, or in a thermochemical equation, you have a delta H. That would be for every certain number of moles, how much heat comes in or out. And remember, the negative delta H means more is flowing out than in, so that's exothermic. Positive delta H, more is coming in and out. So we're gaining heat content in the system, so that's endothermic. If I had to bet just one big connection here, it's tough to say because it's hard to know how many numbers they would give you and which ways they're going to go lab-wise. There's definitely be something with the lab. If it's something with the lab in thermo, it's all about we measure a change in temperature, the change in temperature with the specific heat. with the mass is related to Q, and then that Q is a direct connection to the delta H. Q is how much energy this time in this cup, in this beaker, in this reaction. And then if I just divide it by the moles for that, the Q per mole is my delta H. Do remember that the temperature goes up in exothermic because energy is flowing out to the surroundings or the thermometer itself. That is exothermic, but we do have a negative delta H. The positive delta H would be when it's getting colder because heat is coming in. My heat content of the system is higher because it stole heat from the water, from the beaker, from your hand if you're touching it, and from the thermometer. I think that it's very unlikely to do a calculation from this. This is a pretty simple equation. It's given on the equation sheet, products minus reactants, so be familiar with it. Hess's law is where if I know the heat for different processes and I combine them, I can know the overall heat. That's something we could do math on, but we could also just explain the idea behind it, that if this process is exothermic and this one's also exothermic and we put the two together, it becomes even more exothermic. Or if I'm breaking these bonds, but then I'm making these bonds instead, it gives me that same idea. Calorimetry, like I said, maybe a big one. I think graphs here. Remember, and I kind of talked through this with the breaking and making, the activation energy relates to kinetics, relates to thermo here. The activation energy, that's the energy we use to break all of the bonds and all of the IMFs necessary to start the process. Then it's those separate pieces, intermediate, maybe, if we have a multi-step process. And then I make my products. In endothermic, I put a whole bunch in, very little was released out. So overall, it's a positive or an inward flow. Here, I put a little bit in. I did have to break them apart, but a lot flowed out, a negative flow overall. But in both of them, energy flowed in and energy flowed out. So this is a really good thing to include somehow in your cheat sheet so that you can remember this. But you can't just state all these things as facts. You can't just say, oh, it's exothermic, so breaking is greater than making. You would think it's negative. I had a small amount of energy that needed to be used to break it apart, but a large amount was released as they were made. So that's something, and really putting those into words and thinking about a small amount here, making this a large amount, and all, once again, going back to here, it got hotter. Oh, exothermic. That is my evidence that I can then connect with some reasoning to a claim, whether it's endo or exo, or whether the bond energy of the reactants or the products are greater. So we want to be able to think about evidence, which might be related to something we measure, the temperature. Is it over? No, it's not over. I'm recording right now because Daddy's doing it right now. Why? Because that's how life works now. You can come stay back. Maybe sketching the graph, if you're doing something on paper, would be helpful, but we will not have to draw graphs. You could be given a graph, and that's another way that we can make that connection, but really pay attention to the graph itself. Is it graphing potential energy? Is it the Maxwell-Boltzmann that we did with kinetics? Is it just graphing temperature? Pay attention to those things. Entropy is pretty easy, but it is clearly in topic 9, so it won't be there. Free energy is pretty straightforward, but they consider that clearly in topic 9. The positive and negatives here with delta G's and with those are cell potentials, neither of things that we know about. But do remember that a big K means a lot of products, very few reactants. Yes, that process is happening in the forward direction a lot. So maybe that connection would still help you to remember, oh yeah, way more products than reactants. So the reaction is proceeding. Once again, you wouldn't have to explain it with thermodynamics. It's not wrong to use something that you know, just because it's not in the curriculum they are planning to test. You can use any true facts, any real true facts that you need to in this, but just know that that's not what the intent of the question is. So if you feel like you're going down a delta G path and that's the only way to solve this, you're probably approaching the question wrong. It doesn't mean that you're wrong, but it just means maybe you need to look for some other evidence, some other data, another equation that maybe even would make it a little bit easier. Here, what I did was, it goes back very close to a lab that we did, but it connects some different things here. It shows how we would use data. And I wanted to say I'm quite confident. I was going to bet something, but I have no idea what's on the test. But I would be surprised if there isn't somehow a discussion of an experiment or a presentation of the data table in some way. So whether you had to do these calculations or not, okay, this is our data. We see the temperature goes down, therefore it's endothermic, therefore delta H is positive. We could talk about that. We could talk about which is greater, the total bond energy of the reactants, the total bond energy of the products. Those are things that we could connect. We could talk about the strengths of the acids and bases, bringing this together. We could talk about how to make it go faster and slower with kinetics, with a strong acid versus weak acid, versus a solid that's a big chunk versus a small chunk. Once again, we're thinking about how are they going to integrate a lot of things into one. And another great way to do this would be maybe using this example, but then using a different acid that has a different specific heat, or using more solid or a smaller solution. And they may ask you to predict, would the temperature change be larger or smaller? The numbers can support that. You can have a calculator. You can use numbers and math in your answers. Even if it's not asking for a numeric answer, that's a great way to use evidence and reasoning to justify something, especially if it's something you're really comfortable with. So if I put in more solid, that would mean a bit more moles of reactant, a bigger temperature change. If I had more solution, I would be forcing more stuff to be changing temperature. So the same amount of chemical wouldn't cause as big of a temperature change. So trying to draw those things out and understand them, but really connecting them to that equation. Here, we wouldn't need to justify delta S or delta G, but for delta H, we would need to justify that, or it'd be really easy. Temperature went down, therefore it's endothermic. Because, and we would talk about heat flowing from the surrounding solution, the beaker, the graduated cylinder, into the system or the molecule, the heat content of the molecules and atoms themselves. Thermo is a great place, since we don't have acid-base equilibrium to talk about this, all of it still could be connected to titrations. Let's talk about error analysis. Heat flows out. We lose heat as this is going. So that's an important thing to be aware of or to think about now. Then here there is a sample problem for each thing. If you had to do it with stoic, it's the math, but then some justifications. It's how the math would look for a calorimetry. The standard table, probably not as much. Hess's law, very unlikely to do all the steps. Talking about it, and in doing that, reviewing a problem here, reviewing a problem here, reviewing these problems is a good way of wrapping your mind around it conceptually for some people. Don't worry about our delta S stuff. All of that is entropy. Right there, that's all free energy. Yeah, that's all free energy. I thought there was some delta H mixed in, but it only has the delta H there. So we could draw some conclusions. A negative sign on that delta H does tell us, so I'm not highlighting the negative, that it is exothermic. We can then, even though I'm looking at, well, how many of this and that, I can know more energy is released than drawn in. So it is exothermic. The bond energy of the products, or the downhill, is much greater than the activation energy, the bond energy of the reactants. But this is a combustion reaction here, maybe, if we're thinking about burning it, or it's really just the reaction for iron. But it probably still has a fairly high activation energy. Iron doesn't rust instantly. We can burn things and make it happen a lot faster by adding that heat, or just gradually over time it will happen. Great connection between topics. We can talk about bonds. We can talk about ionic versus covalent versus solids, solids and gases, all within that equation right there. And then down here, there's just some thermo problems. This one I know is really focused on calculations, but it's all thermochem. This one has more explanations. It connects it to bonding, to lattice energy, all of that in a really good way. I included on one of the other videos and assignments we're going to do. It has some ionic bonding stuff here. a little bit less math-based once you get past part A. And we come down here. This one's all math-based, but it's a good way of comparing and contrasting with some simple math. Maybe the numbers that they give you are going to be simple enough that you're not needing to do calculations. You're just needing to have what we call like number sense. You see this number's huge, this number's small. So to do the same thing is a very different amount. What can that mean for us? So that's thermochemistry in a quick nutshell. And it definitely connects, like I've said, with bonding, with kinetics really well. So a great topic to see some of that overlap. So think about those main ideas. Think about what to put on your cheat sheet. Don't worry about entropy. Don't worry about free energy. Focus on the delta H stuff. And hopefully that's pretty simple and straightforward. All right. Have a good one.